Guys, so I think we are recording. All right. All right, so let's get started with the class today. So it's week 3 of the semester. Let's start with the bright space here. Bright space environment, content. Okay. All right, so these are the modules that we're looking at right now before the exam, so to speak. Um, So we've so the we've started the course, right? So practical deep learning. The first 2 weeks we went over agents, um, and we're done with that basically at this point. You've seen kind of how that works. So if you think about how the course goes, it's usually in like the deep learning class or the machine learning class 520, we started from like what is a tensor, we did operations all the way up to code a GPT and stable diffusion from scratch, kind of, and then train it with our own data. So we were always starting with random weights. Now, this course is kind of the opposite of that. We start at the very top, right? The application, solving problems, and then we drill down as much as we need to, basically. But essentially, we're actually using models as they are, if you will, right? So there's been no training so far, and that's called inference. So we've been doing mostly the first 2 weeks, we just did inference, right? And just remember what that means is just using the model to produce something generative, okay? And so currently, the highest that I can think of for that is agents, essentially, right? So where we had code libraries, et cetera, code wrappers, and we using prompt engineering, essentially, we were wrapping all of that around anything from Quen to ChatGPT or whatever it is. So you've seen how that works, and I've given you a glimpse of that. Now, so if you think about agents as being the model and then some code around it, and we use that. Now we're going to peel the layers, right? So we're going to you understand hopefully what the agent code does, and now we're going to start focusing on the models themselves. So that process, if that makes sense. So that takes us then to whereas before the idea was what is an agent, what is small agents, etc., and we were just using something, let's say GPT-2, just to have a concrete example. Now we're just going to look at how did we arrive at that GPT-2, right? What is the process of that? And so or Chat GPT even, right? So that pipeline is going to start from a GPT pre-trained from scratch to have weights to then be fine-tuned, sometimes called SFT or supervised fine-tuning, to a layer called reinforcement learning through human feedbacks. And that process, there's a lot of tricks going on how to do that. Okay, like chain of thought, for instance, which is something that happens at the inference, after the model has been fine-tuned and reinforced, and then maybe you just now have multiple reinforcements, if that makes sense. Like you do one pass and then another pass and another pass. Okay, so that's kind of what we're going to concentrate on now. So just these models, basically. So I will that, and also, by the way, that doesn't just apply to large language models. That can also apply to image-based models, which we will cover later in the semester. All right, so all of that going from a model that's pre-trained, sorry, a model that's not trained at all, that has random weights, and giving it lots of data to arrive at a model that has been trained is called pre-training, the pre-training stage. And then after that, we have the fine-tuning stage. Okay, so today we're going to focus on that. So we're going to look at this. My plan for today is to look at this module here during the first half of class, and then we're going to look at this module here for the second half of class. So if you look at, hopefully you've been paying attention to the news and you've heard about DeepSeek R1. And so I will talk a little bit about that. I've already provided the papers that I want you guys to start reading about. And so I'll do that during the second half of today to give you some context. So this is because there's actually a lot of very important ideas there, both positive and negative, right? There's all kinds of things going on. But before that, I want to start with Hugging Face Transformers module here. So obviously this is the Vaswani paper that I've added. Read it, right? Start reading that. I still need to add two more papers, which are going to be the actual GPT paper. So I will provide that. Those are papers from 2017, 2019, and possibly the BERT paper, although I do have a here, BERT module. So I'll probably dump that paper in there. Okay? Makes sense? And then there's going to be, so this course, as you can see, involves a lot of papers to read. Now, how do you approach these papers? Do you need to memorize them, every detail? Of course you do. Okay. So how do you, so really the way that you should approach one of these papers is there's the idea that they're trying to tell you about, and then there's the details of it. There's also the reporting of the performance. Basically, if they say that it works well, I mean, glance at the tables because it did well, right? That's what they're saying. So, and it's an important paper. You know it worked. So really what you have to do when you read one of these papers is just always ask yourself this question. Do I understand what they did? Do I get the gist of what they proposed and what they did? Once you answer that question, you can pretty much stop. You know what I mean? Because everything else is just going to be details and so on and so forth. So I'll show you an example of that with the DeepSeek paper, all right, of how we can go about that as far as reading these papers. Okay, makes sense? But yeah, so I wanted to have one starting paper, and I think attention is all you need is kind of the foundational paper for LLMs. And so let's start there, but it's actually technically not a transfer learning paper. It's a different kind of paper. So just as I said, don't memorize all the details, just kind of learn. And eventually at some point I'll ask, we'll have like a discussion where we say, okay, what did you like about that paper and so forth. All right. So anyway, as I said, I want to add the GPT paper here, and I haven't added. So today, some of the examples we're going to do. So as you can see, we're still at the inference level. All right, so we're still going to be doing inference today, but what's coming is we need to learn how to train these models, and we need to learn this idea of fine-tuning. Okay, so I will provide I have a PDF that I'm going to go through today just to give you kind of the terminology and what everything is. And then after that, basically we need to do some, whereas before, let me give you this contrast. Whereas before, let's say in 520, we would start with a model with random weights and train it. Now we start with a model that has some weights and we just continue training. And that's called fine tuning. And beyond that, there's very nice techniques based on reinforcement learning. I alluded to some of that in the last class, and we're just going to continue to explore that idea. Like someone mentioned reinforcement learning, but there's more, it's a very complex area. Okay? Makes sense? So that's kind of the plan. And as I said, we'll do that with images as well, using the Fast AI library. So I have some examples of that actually as well. So as we start to get into the idea of fine-tuning models, right, that's going to require a lot of computing power. So I need to have the the cloud for that. So I need to work on that to provide that for you guys to do the fine tuning. This is not something that you can easily do on a laptop with CPU. So just be aware. But so far, at least today, we can still do this on our laptops because we're only doing inference. We're going to be using the models. Now, so to do that, the library that I'm going to start. Pardon? Oh, yeah. And I'm okay. Yeah, that's a good point. I did record. I am recording it. Sorry about that. Thank you. what was I saying? I think I was saying that the library that I've chosen is uh, Hugging Face transformers. There are other libraries. Replicate, for instance, is something that we can play with later as well. And that's mostly for images, although we can do it LLMs there as well. But I'll start with Hugging Face. It's a pretty important one, pretty important library, very powerful. Keep in mind, these things change constantly. So, some example that I may have on my GitHub may have changed a little bit, right? And so, but we'll work through some of those. So today, I'm going to give you some of the basics of just the Hugging Face library. We're going to use it, get the gist of it, although we've started using it already. And today, we're just going to use it a little bit more. And then this is the library that we were going to need to do, fine tuning and reinforcement learning. Okay, it's basically one of the best ones right now for doing this kind of thing. It's a company, I think out of Europe. It's well supported, like 200 engineers or something like that. All right, so I do want to give you some. So these are the links for the code, probably my GitHub. I think this is the link to actually Hugging Face. This is the paper that as I said, start reading through this one. And I will also add the GPT paper a little later. And I provided here a PDF of some of the terminology for transfer learning, essentially, right? So we're going to start there. Transfer learning, what are some of the terms? There's a lot of terms, actually, a lot of ideas. So it's, a machine learning model used to be just, okay, here's some data, train it, evaluate it, done. But now there's so many additional ideas that are going on. And so there's, for instance, a term called distillation, right? And what is that? It's basically taking the knowledge of one bigger model and passing it to a smaller model, like a teacher to a student. So there's lots of ideas going on. So I'm just going to go over some of the initial terminology. And these are my notes that I prepared in the PDF. So essentially transfer learning, right? What is that? So as I said, it's the idea of utilizing someone else's work to build a better model, borrowing their model, taking data from their model, lots of ideas. And this doesn't include all the terms, but it includes some of them. So transfer learning is one of the most important developments in AI since transformers. Transfer learning is an approach where you pre-train a model with some data, usually a lot of data, right? So this is the kind of thing. So if you think of GPT-4 or Llama 3, I don't know DeepSeek now. I don't have that statistic yet, although I've been reading the papers. But GPT-4 certainly, it's like the whole internet, right? And tons of books and just lots of information, even synthetic data nowadays. And then they go back into those, let's say something called Common Crawl, which is all the web. They go back and extract more information out of there, but that's more specialized. Like for instance, how to solve math problems, right? So there's a lot going on. But the data sets are really large. Okay. So to pre-train a model, it's basically currently the official information is that it takes thousands of GPUs, massive amounts of data, lots of money, millions and millions of dollars to train one of these models. DeepSeek just came out and they said that they did everything with $5 million. And whereas before it took $100 million, they did it with less. Still not clear, right? So, but it seems legit. So keep that in mind. It changes a lot, right? Like immediately 2 weeks ago, I would have said one thing. Today, I'm kind of obligated to say something else, right? Because we just don't know. But certainly so what I think I will do is I'll talk about this as it was 2 weeks ago. And then when we talk about DeepSeek, we'll think of why it's such a big deal. And it is a big deal if all is accurate. So the models are pre-trained. So that's the term. So whenever you say pre-train, you're basically starting with a model that is huge, first of all. Like it's a neural network. You all know what a neural network is. Hundreds of layers, right? Blocks, etc. 70 billion parameters. That literally means 70 billion weights and biases. Think about how big that is, right? The other day I was downloading a file of just the weights, and I think it was 7 GB or something like that. So, or maybe it was 700 gig. I don't even know anymore. The values are so astronomical, right? So that's a lot. Imagine, right? And so the models are really, really big. So that's pre-training, right? It's going from random weights to an actual set of weights. But still the model, it's kind of like it knows how to complete things possibly well, right? So it might have good grammar when it produces things, but it really doesn't know what to do. It just kind of doesn't know how to follow instructions. It doesn't know how to do tasks. It doesn't know how to answer questions, right? It just generates sequential text, but the more you have of it, the more correct it looks, at least if you look at it from a grammar point of view, etc. That's when you have something called fine tuning. And with fine tuning, what happens is now you have a specific task. So the way that this started out is just the classic example of sentiment analysis, right? So that's literally where it started. So just a few years ago, all you could do is like, okay, it generates good text. Now let's give it some text and it's going to tell us if happy or sad. And that then named entity recognition, summarization. These are some of the examples we will do on the on when we look at Hugging Face transformers module. But now, obviously, you have seen from the last 2 weeks, I showed you examples of instructions, right? So you can give it a set of instructions and it does something, right? Or math problems, right? So solving math problems. So all of that would be under the realm of fine tuning, taking a model and now training it to solve a math problem or, follow instructions as you have seen. So we'll see every one of these things. It's a paper essentially, right? One of the example I have at the end of class today with DeepSeek, I don't have the full code yet. I don't think anyone has the full code, but I have what I think is kind of what they did in chain of thought. So we'll take a look at that. Kind of almost pseudocode, although it's in Python. But anyway, the distinction is you have pre-trained with lots of data, and then you have fine-tuning of the model. So for instance, because of the size of these models, what I'm going to use a lot is GPT-2. GPT-2 is not great, but it is a free-trained model, right? And so we're going to take that GPT-2 and then fine-tune it, for instance, with SFT for some tasks, and even do reinforcement learning with it, okay? Just to kind of underscore how that works. And a lot of the time, it's better to leverage as I said, the Hugging Face transformers library. So, and then fine tune the same model with less data, but for a specific task. So this is important. So the data can be a lot less. So like if you had, let's say, 100 billion tokens, of text for pre-training, now you have 1 million tokens for fine tuning, a lot less. Another way of thinking about it, you have like, I don't know, massive amounts of data for pre-training, but 100,000 examples for fine tuning, a lot less, more specific. And one important thing is that the quality of that fine-tuned data should be really good. Okay, really, really good. So this allows companies, entities with vast resources to pre-train the models, and then they can later share with others. All right. So this is the big companies that have done these models. Qwen is from Alibaba, right? It's a Chinese company. We've got GPT-4, which is OpenAI. Llama 3 is from Meta, which is Facebook. Now DeepSeek, their DeepSeek base. I think they pre-trained it. I'm not entirely sure. But they also applied their technique to other things like a llama, I believe. So only very large companies have been able to do this so far. pre-train these huge models. GPT-4 is not available. Llama 3 is, right? So we can, but I think we ran it in Llama the other day, but it's a really big model, basically. So yeah, so they basically so far the pre-trained models are created by large organizations, but then we can take those and fine-tune them. So in the class, I mean, you can take a Llama 3 or something like that and try to fine-tune it. That's fine. The problem is, will you have enough resources, right? I don't know if the GPUs that we have available are going to be powerful enough for something like that. But as I said, GPT-2 is something that we can use. And for instance, one example that I've done in the past is we have a GPT-2 that generates whatever text, and then we can make it so it generates text that's a little bit sadder or a little bit more like horror movies. You know what I mean? So we can definitely see the change, right? It's not going to be as good as ChatGPT, which can write a really nice piece of text, if that makes sense. But we'll be able to see the effect. Okay, so that's key. So remember the course, transfer learning, pre-trained, fine-tuning, and then beyond that, other ideas. So training with massively large data sets requires a lot of resources, such as computing power, money. You know that there's even something called export controls going around, right? So, you know, people can't even, other countries are not able to get more than, I think, 50,000 H100 GPUs, and you need way more than that. So it's a huge competition and a huge problem that this creates. So it requires huge computing power, huge amounts of money, and can currently only be done by large institutions and companies such as Google, Meta, etc. So here I kind of have a list. This does not include everything. I mean, I wrote this probably like a year ago or so, and there's like 20 more new terms. So, but anyway, some important ideas in transfer learning. This is kind of how I have it now. Some of the most important, I've defined pre-training and fine-tuning. You should know what that means. There's this idea of freezing some weights on the neural net. So this is going to be one of the ways that we can fine-tune a model. So you have a model that starts at the input layer, and then it works its way up all the way to the final layer. So what you assume is, and images are good here, you give it an image, and the first layers are like filters that are extracting things about the image, like curves, circles, squares, shadows, all that stuff. And then other layers use that information to understand them. So really, you don't need to change the first layers. But once it goes through, let's say 70, 80% of the layers, then you have a representation of the original image that has a lot of semantic meaning in it that is helpful. And then you take the last few layers or add more layers even with random weights possibly. And when you're training your problem, you give it the input, it goes through the trained frozen layers until it gets to an output that now can go into these final layers that have random weights. But remember, you're doing some task like predicting, you know, a label or predicting an answer or whatever. So that's what you train on, right? So you give it, freeze some layers, and then only the last layers need to be updated, if that makes sense, based on the feedback or the results that you get in the task that you're doing. Make sense? So if you have an image and you want to generate a poem from it, right? So it goes, at some point it starts generating that poem, and then you compare it to a real poem, I suppose. And as it starts to get better at it, you know, that means that the weights are getting good as well. Does that make sense? So that's one of the ideas. So that's freeze some weights with the neural network, sharing the weights from one model to another. So this is another idea. This is a nice one. So for instance, so essentially what a large language model is just the architecture of a neural network. And then each one of those connections is a weight or a bias or something. So those are called the parameters. And you can literally just train your model, make the weights available. And then now let's say in an example, like you want to build a robot, you code it in C even, not even in PyTorch. As long as you have the right architecture, right? Then you know that, okay, I need this weight and this weight. You can download the file of the weights, load them into the network that you wrote, and that's it, right? So that's essentially. So I think somebody made the funny joke when they were really afraid of, like, are these large language models going to kill humanity? They were making the joke, well, you're just afraid of a file full of weights. That is the thing that's going to kill you, right? Because essentially that's what a model is, right? One of these intelligent models. All right, another term. Well, obviously, transfer learning metrics are we need metrics. So just like before we had precision, recall, F measure, and you're all familiar with those. You know, I need to provide this paper for you guys. There's a new set of metrics, and you have seen some of these especially in these reasoning models, right? So these reasoning models, for instance, you give them at this point, you give them questions from the SAT, right? Or you give them math Olympiad questions, and these are the metrics, right? So they measure how well they do on these competitions. It started with, like, in the 2017 paper that you're going to read, the Vaswani Attention is All You Need paper. Basically, that was for language translation, and the metric used there was the BLUE, the blue score. So that metric was literally designed to measure how well a model translated from one language to the other. All right. So the point is, it's machine learning. There's fine tuning, training, etc. We still need metrics, and these are highly specialized metrics. As we look at the paper and we look at the performance, that's what we're going to be looking at. There's, as I said, there's other terms like distillation, and other things that I don't have in this. I'm still working on that document, so I'll be providing that in a future lecture. But there's more terminology, okay, of things that are happening. Now, the other one that's huge is this one: reinforcement learning through human feedback. So this comes from a field called reinforcement learning that has existed before LLMs and deep learning. So an area of artificial intelligence, really, as far back probably as Claude Shannon in the 40s, where he did his first little robot thing. And so reinforcement learning has been a huge field, right? And then there's reinforcement learning through human feedbacks, okay? Which is, we'll talk about that term as well. And actually, one of your assignments will be to use reinforcement learning through human feedbacks. It's a really important one. So I have here some definitions of each one. So as I discussed already, pre-training is the process of training a model like a large language model with massive amounts of data. So weights are from scratch. The best models have been the ones pre-trained by large organizations. Pre-training starts with a model that has had no training and where the weights are usually initialized randomly. The process can take many months, require multiple GPUs, and I mean thousands, not 4. I think it'll be interesting for you to read that Vaswani paper, because I believe in that one, they were using only 8 GPUs, a motherboard. It was not a cluster of computers, but just one computer with a motherboard that held 8 GPUs. You pay attention to that, because that's really important. In transfer learning, the hardware is huge, okay? So I'll talk a little bit about that as well, about what I mean by that. But yeah, massive amounts. But it started at 8 GPUs probably. You guys will have 1, and today is 1,000, okay? And training needs to be performed on distributed GPU systems, which is not a trivial thing to do. This is a very specialized skill that I encourage you to learn, because, it's really important. So you start with code such as that of the GPT algorithm. Those of you that took 520 know exactly what I'm talking about, right? So I gave you the GPT code and you train it with some web scrape data. You essentially did that scenario of pre-training, but on tiny everything. And the code doesn't actually change. So the code is not what changes. It's the same algorithm. What needs to change is the amount of data, number of GPUs, the amount of money, essentially. Yeah. All right. So I've set that fine tuning. also known sometimes as supervised fine-tuning, SFT, which is the terminology that you'll see a lot, is the process of taking a pre-trained model with pre-trained weights and performing some additional training on it. Here you want to reuse as much of the pre-trained, weights as possible. As I said, one scheme for this requires freezing some layers of the network so that those corresponding weights are not changed during fine-tuning. Okay, so that's kind of the idea. Also, a trick is the learning weight. So the learning weight could also be very, very tiny for some of the layers and then much bigger for the last layers. So that's another technique. These things have different names as they are being experimented on. Fine-tuning can be done on one GPU, at least currently, right? So that's one, as you will see in the course, with one GPU, you should be able to fine-tune a GPT-2. It'd be nice if you try to fine-tune a llama model or something like that. So that'd be very interesting. And may not require massive amounts of data. So for instance, DeepSeek, I was reading that I believe they use 800,000 examples, and that would be considered small, right? So at their fine-tuning reinforcement learning phase. So 800,000 examples of how to do a thing called chain of thought reasoning with math problems. So yeah, that's smallish at 800,000. Okay, so may not require massive amounts of data. It is usually focused on specific tasks like sentiment analysis, question answering. You can see, maybe I wrote this like 2 years ago, and that's really all I was focusing on back then. Now it's solving math and doing tasks, and so this has moved really fast, actually. Like it's amazing. All right, so I have some code examples here that we can look. Oh yes, please, sir. Go ahead. Yeah, exactly. So like the example I gave with images. So images is a good example, right? You take an image and you extract circles, shadows, squares. All the first layers are really good at that. But that's not what you need for whatever task you're solving at the end. And so you're taking advantage of that understanding that it has. So in language, maybe it already knows what a noun phrase is and a verb phrase, and it knows what a determiner is. You see the past tense of a verb, and now, so it knows how to do all that. It just doesn't know how to solve math. You see that? So you're leveraging that. It's another way that people say it is, you want a GPT-4 that's a physicist. It already knows how to speak English, but it doesn't know how to solve physics problems. And the fine-tuning might give it that. Got it? Great. Excellent. All right. So as I was saying, I do have some code examples here of some of these ideas. And like, I just want everyone to be clear on this. So freezing some weights of the neural network. When performing fine-tuning, freezing part of the weights of the model may be required. This process can be seen in the next code listing. So here's an example of what I mean. So freeze the first 70% of the hidden layers of the model. So basically, this is a model, a GPT dot transformer, right? You figure out the number of layers, you print it, and there's 12 layers, essentially, right? So this is a small model. And now you tell it the number of unfrozen is going to be just 30% of that, right? So like 3 layers, basically, or something like that. So then you just you have the layers kind of in like an array here. So you can say 4 layer in layers, right, until that point. And so you start grabbing that layer as an element from this sort of list. And what do? You just say layer dot requires grad equal false. If you guys remember from 520 and when you're doing deep learning, right, when you're training the model, we say requires grad, which basically means what? That when you're doing the loss and the backward steps, you're going to calculate the gradients for the update of the weights. If you say if requires grad is set to true. So if requires grad is set to false, then what does that mean? That you're not going to calculate gradients and basically those weights are being ignored. Does that make sense, guys? So that's basically freezing in this case. So we're taking the 12 layers that we have here, we iterate through them, we literally grab it, and we just changing that one parameter freezes them, essentially. Got it? So now we have the network here, but it's not going to be when we do the training, those layers are not going to be changed. Here we can check. So we can take model GPT gen, some name parameters. And so we're going to look at all the layers and basically print the requires grad. So you can see here, notice that in the previous code listing, we iterate through all the layers and change the parameter layer dot requires grad to false for all the layers we want to freeze. The result of freezing can be seen below for a GPT-2. And so you can see here now, this is the transformer, layer 0. I didn't put all of them, but layer 0 to layer 8. And you can see false, false, false. And about here, layer 9, it says true. All the way to 11. So it starts at 0, which would be the layer closest to input. And layer 11 of this GPT is closest to the output. So essentially, we just changed the requires grad, and these are now frozen. We can fine tune it, and they will not be changed. And that way, the understanding of language, of grammar, or of all that persists, and we only modify the last layers that are closer to the prediction that we want to do. Got it? This is in Hugging Face. This is usually adding what is called a head to the GPTs. So this happens a lot too. You can take a GPT, remove whatever it was doing at the very end, like the last layer, and then you couple in there a head, and that head can be trained for some specific purpose. So there's two ways that we can do this. We could do this from scratch in PyTorch, or we can do this through the Hugging Face Transformers library. The Hugging Face Transformers library obviously makes it a lot easier to do, but we just have specific constructs that they provide for these tests. Does that make sense? So that's one of the things that we will cover, not today, but in future classes, is how to do fine-tuning of a model, a GPT. All right, so that's any questions about this idea? All right, so that's freezing the weights, and you can try out that code if you'd like. Sharing the weights, you've seen this quite a bit. There's a couple of ways of doing this. So there's something like torch save weights, and you save a dictionary, I believe, of the weights. But sharing weights is very important as it allows pre-training to be done only once. After that, only some modification to the weights needs to be done. In Torch, the weights can be extracted easily using, for example, the function model.parameters. I literally was looking at DeepSeek, and there's something called llama.cpp, and that allows you to define the architecture of a neural network, and then basically they've made it available so that you can download their weights for their DeepSeek model. So it's a really large file. It's a lot of data, but this is a common practice, sharing the weights. Currently, there are specialized libraries that help share models. These include Hugging Face's Transformers module and also FastAI. So we will use FastAI for some image examples later in the semester, and we will. But right now, we're looking at language. Any questions? Okay. Now, reinforcement learning through human feedbacks. This is a massive topic, but I will provide a paper for this one as well. The idea is this. It's really, this will be one of your assignments for sure. So the idea is this. you're playing a game, right? Let's start there. You're playing chess or something. So what happens is you have an agent, some software that needs to play in an environment that has rules, right? And then that software takes action, such as move the knight to here, to one position over here or over there. Once that happens, that is called a state. That's given to the environment, and the environment gives a reward. Now, in games, that's really easy because games are basically board games, right? I'm talking about board games, and they have specific rules, right? Like if I move the knight here and there's a pawn there, the next move obviously is that the pawn's going to kill it or the queen or something like that. So you can actually hard code the rules with a lot of if statements, right? And then based on that move, the environment provides what is called a reward, which is nothing more than saying, okay, for that move, I give you a 100. For a bad move, I give you a minus 50, so on and so forth. The problem is that's reinforcement learning alone, right? So that's the scenario. Agent plays in an environment, there's a state, takes an action, you get a reward, and then based on that, it learns how to do that. So we'll cover that. But the problem is there was a lot of advancement that was made with reinforcement learning all the way to AlphaGo, which AlphaGo is based on a game, a Chinese game, I believe, like chess called Go. That's much more complex, actually, than chess. And they were able to create a reinforcement learning based model that beat that, the best player in the world, some guy, Sudal, I think, and he lost. And now computers are better at Go than humans. So obviously, wow, amazing potential. That was actually published in Nature, which is, only amazing breakthroughs get published there. But the difficulty with that, reinforcement learning is amazing. The difficulty with that is the reward function. The reward function for a game can be coded, with if statements even. But now so there's, people at that moment are all excited, but then they think, oh, wait, but how do we use reinforcement learning on a large language model? Do you know what I mean? Or our robot. And now this, look at this example. Let's say you want to teach a robot how to dance salsa. What's the reward function for that? Do you know what I mean? How do you code a reward function to say, yeah, you're to teach a robot how to dance salsa, right? So that was really difficult. But then somebody invented this idea of reinforcement learning through human feedback. And what that means is let's not manually create the rewards. Okay, and that's the idea. And like I said, these ideas change and evolve, but essentially this is the idea of this, that you don't want to create the reward function manually with if statements. So then what other option do you have? Well, we have a model that's a neural network doing actions, right? We know that. And then we were giving it reward via if statements, and that worked really well for AlphaGo. But the problem is creating those rewards manually by a human is really hard. So somebody said, okay, how about this? We have a neural network that takes the actions, and we're training it. And for the reward model, let's use a second neural network that's separate. And we're going to teach that neural network to provide rewards. And we don't even know how to create it. We're just going to train it in some way. Do you see what I'm saying? And that's what reinforcement learning through human feedbacks is. Essentially, that you have now two models, essentially one helping the other to learn. You care about the one that's learning, right? To dance salsa, but you need the reward model to give it feedback, and it needs to learn. So how does it do that? Well, very clever, actually. Going back to this idea of dancing salsa, you have the robot. You have a function that's supposed to give feedback. So what they came up with, have the robot randomly move its arms and legs, right? Weights are being adjusted and it's moving. As it's training, have it generate 3 short clips of it doing that randomly. Do you see what I'm saying? So then you look at one clip, you look at another clip, and a third clip. And then here comes the human feedbacks part. Then a human will look at all three and say, the third one is better. I mean, they're all terrible, but this kind of look, at least it moved its legs, right? And after doing that, you're essentially annotating a data set. That then, so essentially the reward model is almost as simple as a classifier sometimes, like any classifier that you guys have ever worked on, Iris, if at all, right? Or MNIST, so essentially you're just providing that little feedback. So the next time around, well, the model got that feedback that whatever it was doing with its legs was great, but maybe flipping their head in 360 degrees was not a good idea. So it stops doing that. It flips the legs more in one direction or another. 3 new videos are generated, and the human, because humans, and this is something pretty critical, it's very difficult to generate something. It's a lot easier for a human to look at something and say what they think about it. Do you see what I'm saying? So I do this a lot. I ask ChatGPT, if you tell me write DeepSeek right now from scratch, I'm like, I can't do that. But if I go to ChatGPT and I tell it, hey, ChatGPT, do you know this paper? Yes. Can you give me some code that kind of looks like what they're saying? It gives me something. I read the paper and then I look at it. I'm like, yeah, this seems to capture the gist of it. Do you see what I'm saying? So it's much harder for me to create that script from scratch than it is for me to get something and look at it and say, or get 3 of them. ChatGPT gives me 3 versions of DeepSeek code, right? And I've read the paper. I'm going to go, well, I think this one. And then, and so that's the same idea. And so that's what reinforcement learning through human feedbacks is. And this has been game changer, okay? This is probably, although people criticize RLHF and RL in general, this has been very significant. The original ChatGPT that you guys had that moment in 2022 or whatever it was because of this. And then now we have other things, but it's still reinforcement learning. DeepSeek is still reinforcement learning. And we'll talk about those ideas as we move through the semester. But the original paper, you need to understand, which, as I said, I need to provide it, and it's going to give that salsa example because they started with robotics, and that's where they were at. AlphaGo, great, but it's a board game. A robot is totally different, right? How do you code a reward function? So anyway, the reward, so as I was saying, creating the reward model is difficult. Creating a heuristic-based rewards is difficult. Having a neural network provide rewards given human preference data, as it's called, training data, is a lot easier. And then after a while, going back to my original analogy, as I'm going with salsa and I'm going, oh, this one, I do that. I don't even have to do that forever. I do that for a while. And after a while, what happens? You've collected all this data, you train the model, the reward model, and then now you use that reward model alone. So maybe imagine this, like they hired you and for a month, every day you were doing that, right? But then that data collected that month is, give me a second, is used to train the model. The next month, now only half the time do you get, you have to label, the other half is being done by the model. And you can assume that that's going to be 60% accurate. And you just keep like polishing that until eventually, hopefully that reward model is really good. And we have seen that it works because we see the examples of the models. Yes, sir. Yeah, so it would be recommended that you get more than one person. I completely agree with that. For instance, in ChatGPT, I think we'll see this too. The classic example of this with ChatGPT was what? Questions and answers, right? And what happened was a GPT, you give it a question, it gives an answer. So what they would do is they would take those two, concatenate them, and then they would feed them into another model, which would say good or bad or whatever it is. but they would also give that to a human. So a human would get, for one question, 3 answers, and they just said, this one's the better one. And that data feeds into the network. Obviously, having multiple people doing that, and I think that's where they spent a lot of money actually with OpenAI. They probably hired, because they hired really good people, because it's key to have good data when you're doing that task. Is it really doing that still? Okay. Yeah, I think I have had one example of that actually with ChatGPT. But yeah, and so right now, for instance, that ChatGPT is deployed all over the world, and you guys are doing that. I guarantee you, they're taking that data. Anything that's happening, like clicks, amount of time you're there, amount of interaction, they're measuring all of that because they know that if you're engaged with it and you're like the questions you're asking seems it is the feedback that you're providing that you like what it's giving. And so they're going to use all of that to train reward models that are fully automated and so on. But that's the mechanism. So RLHF is a key component. Any other questions? And as I said, we will do coding with this one. There's a Transformers RL, reinforcement learning library of Hugging Face, and we can use that. So I will ask you to take GPT-2 probably, or better, and just make it so you will do this exact scenario. You'll have to train, so there's another trick. So there are in fact models right now. So for instance, there's a model for toxicity. So what does that do? It takes text and it says this is very toxic or not toxic at all, right? So that's a model that exists already in the Hugging Face library. So you can actually use that model in an RLHF scenario because you can take a GPT-2, right? And you can start training it to produce new text, use that model to say, how toxic the produced text is, and then based on that information, adjust the weights to maybe make your GPT-2 less toxic, or for whatever reason, you may want it to be more toxic. Either way, you can do that. You see that? You can change it to be of a specific sentiment. You can change it to be like in the past, students, I like one project they did where they had text that was generated, and then after the RLHF, the text had more horror sounding things in it. They made it more or you could change it to be maybe funnier. That's also a possibility. If you have an RLHF, if you have a model that takes in text and tells you how funny it is. So then you could use that to train the other model to be more funny or less funny. It's not going to be perfect because a lot of it depends on the GPT-2, but you can essentially see the impact of it. And as I said, if you have more resources and use a Llama 3, you just have better results. But it's a much larger pre-trained GPT. Is this making sense, guys? Yeah. All right, great. So we will, today one of the things I wanted to do is just go over a lot of this terminology so that you're well situated. But we will do some coding examples. So let's go through the text in case I missed something, but I believe it's what I've said. So RLHF is a technique from RL where you train a model by providing it feedbacks. Since manually creating a reward function to create feedbacks is very difficult, this can be done by replacing the reward function with another neural network, right? So that's what I was saying. And they're separate. So they're 2 different neural networks. And one is simple. Although actually I should say at some point, they can also be 2 GPTs, right? So one is the GPT that's generating text, and then the other one can be a GPT because obviously, think of what's happening, right? So you have the GPT, the question goes in, answer comes out, which is text. So for the reward model, what do you need? You need a GPT that will understand this text as input to produce an output. So what might be simplified is that this is just a classification at the end. So 2 GPTs. Now keep in mind though, here comes in a difficulty. Before, you were trying to fine tune at one GPT, and that was already really hard. Now you're trying to use another GPT to give feedback. So essentially, you doubled the difficulty of your problem because you have now this GPT and this GPT, and both of them need to be trained correctly. They may be pre-trained, but they still need to be fine-tuned for that task. Do you see that? And so that actually is a lot of what's going on with DeepSeek. Okay, so people have been using this model of two GPTs, one for the actual and one for the fine-tuning, but that's difficult. And it's been like in the last year and a half, this competition to simplify that. And one of the solutions is literally to just get rid of that reward GPT and solve that problem in other ways, because you just are left with half the complexity, if you will. Make sense? So my understanding with DeepSeek is that they didn't use two models. This reward model was heuristic based, which is crazy because we were getting away from that. And somehow they're saying that they went back to that, but in a clever way. I don't know. You'll need to read the paper and we'll see how things develop, but this stuff just keeps changing. So it's very, but I do think this one concept is really still very important, and the reinforcement learning through human feedbacks. This data is usually called human preferences. So for example, we can train a GPT to generate more positive or more negative movie reviews. Now the process involves giving text prompts about the movie to the GPT, the first GPT, in order for it to generate text responses to those prompts, right? So that's the first GPT. These generated text responses, the movie reviews, and the original prompt. So notice it's both that are given. What the input and output are concatenated, and the original prompts are concatenated together and given to a reward function for evaluation. The reward function will assign a score to the input text indicating how good it is. The reward could be based on heuristic rules, which is what I was saying, that's how it started, or a model that uses human feedbacks. A clever approach is to use a task-specific BERT model. And BERTs are like GPTs. They're just transformers at the end of the day. But I'll talk about BERTs in a couple of weeks. But essentially, a clever approach is to use task-specific BERT models to read in the GPT-generated text and assign a score reward given this text. So today, we'll see an example, actually, of something like a BERT that does sentiment analysis. So you'll get an idea of what I mean. As such, the BERT model can be used as a reward function. Okay? Because if you remember in your machine learning, you're not actually just providing cat, dog, bird. You're providing what is called a logit, right? Which is the vector, which provides the probability distribution of what that is. So, 95% cat, 2.5% dog, 2.5% fish. So that value, that 0.95, is like a reward because it quantifies from 0 to 1. You see that? So that's a really key aspect of it. So essentially today we're going to look at something that is like RLHF. All right, that concludes RLHF. Are there any, at least the basic introduction of it, any questions on this? Making sense? All right, so keep in mind, as I said, you will do a assignment on this one. Transfer learning performance metrics, I did not include all of them. I did provide the paper there, so thankfully. So since fine-tuned models are highly specialized models that can perform special tasks such as translation, summarization, math problem solving, instruction following, etc., they may require new special metrics for performance analysis. Some common metrics for this can be seen below. So blue, that's the translation one. WR is called a word error rate. The glue score, I think it has to do with semantics, and many, many, many more. In fact, a paper from 2021, which is probably dated by now, I recommend that you take a look at that one. A great survey paper with many of these types of metrics can be found So just look it up. So these are the authors, 2021, and it's a survey paper. Again, I don't expect you to memorize any of this, but if you want to understand these a little bit more, go through it. It probably does not include the new metrics for reasoning and math solving and all that, which is, I'm sure, in some other paper. All right, so yeah, that's I think that's the initial terminology. As you probably know, I didn't cover all terms like distillation, etc. I will probably create another document where I have a few more of the terminology. But hopefully this gives you some intuition, right, of what's going on. All right, so I think, so we have some time, about 30 minutes. So in the next 30 minutes, what I want to do is just go over the Hugging Face Transformers library, okay? Again, we're just going to be playing with it so far and doing some inference and seeing how it works. And then after that, we are going to take that library and just our very next example is going to be to fine tune it somehow for some task. Okay. All right. So so that I can close this document, I think. So that's basically the whole thing. So let me actually pause.